Hello everyone. This is a group presentation on Introduction to Operating Systems, which is a fundamental topic in computer science. We begin by defining what an operating system is and what it does, what are its functions and what is its purpose. We then move on to evolution of operating system over the years, from performing simple calculations in the 1940s to performing complicated multitasking operations, as well as having sophisticated modern day interfaces. Then we will see types of operating system on the basis of constitution and separation of components, as well as on the basis of memory management, wherein we have multitasking as well as multi-programming. And then finally, we will see different modes of operating system, which is the ways in which operating system works. In that, we'll see an overview of user and kernel modes. So we begin by defining what an operating system is. Well, in a nutshell, an operating system acts as an intermediary between the users and the computer hardware. It's a program which is loaded initially in the computer by another program called a boot program. It manages all the applications inside a computer. Here you can see an operating system acting as a medium between applications as well as the computer hardware. An operating system is very beneficial to the computer and the whole area of software development. And you might ask why. Well, without an operating system, each application will need to implement its own user interface. It will need to handle all the complicated machine code by itself, by which it will access the hardwares and manage the disk storage, also manage the interfaces, network interfaces, which is handled by the operating system for them. Now we move on to the functions of operating system. What are the different functionalities an operating system has? We have process management. Operating system manages different processes by creating and terminating them. It also schedules different processes, which is something called CPU scheduling, by different algorithms like first come, first serve, round robin, etc. And it also handles the important task of CPU synchronization or process synchronization through something called semaphores, etc. Then we have memory management. An operating system manages the memory of a computer system. It tracks, it allocates, and it optimizes the memory. It also assigns memory to processes by something called paging, segmentation, and virtual memory, which are the different procedures to do the same. It also takes care of memory protection as well as swapping, which are some of the key features in memory management. Then we have device management. An operating system controls hardware and their users. It also facilitates communication between the different devices, and it also handles the input-output operations inside a computer system. The next essential functionality of an operating system is file system management. It essentially creates, deletes, manages access control, permissions, and data integrity of different files. It handles data by organizing it, restoring it, and retrieving the data. Then we have security and access control. Now, an important functionality of operating system is to implement authentication as well as permissions for the user so that an unauthorized access can be prevented. And it does the same very efficiently. Then we have the user interface. An operating system provides graphical user interface or command line interface by which an user can interact with the system. And then last but not the least, we have networking. An operating system facilitates communication between the devices over a network. So in short, operating system is an incredible resource manager. It optimizes different resources, be it processes, memory, files, or different hardwares, Now that leads us to another aspect of our presentation, operating system as a resource manager.
OS as a resource manager. At its core, the OS ensures that the hardware and software resources in a computer system are utilized efficiently, distributed fairly, protected from misuse. Let's explore the key roles and functionalities of the OS as a resource manager. Resource allocation and management, CPU scheduling. One of the critical tasks of the OS is managing the CPU, the brain of the computer. The OS schedules process using algorithms like round-robin scheduling and priority scheduling. Round-robin scheduling allocates CPU time to processes in equal slices, ensuring responsiveness in time-shared system. Priority scheduling assigns the CPU time based on process priority, allowing more critical tasks to execute first. Efficient CPU scheduling reduces idle time, improves system responsiveness, and ensures smooth multitasking. Now, I'd like to talk about memory management. The memory management is another essential role of OS. It ensures each process gets the memory it needs without interfering with others. Paging and segmentation is also ensured. The paging divides the memory into fixed size blocks to minimize fragmentation. Segmentation divides the memory into logical sections like code, data, and stack. By optimizing memory allocation, the OS ensures that the running process have resources they need while maximizing available memory. Storage management. The OS manages the device storage through file system, which organizes and controls the data stored and retrieved. Key responsibilities include ensuring secure access to the file directory, handling data storage across devices like SSD and hard drive, support multiple file systems such as NTFS, FAT32, ext4, and effective storage management system prevents data loss, ensuring efficient file operations. Now, I would like to talk about maximizing resource utilization. By balancing the workload, the OS ensures all hardware components are used effectively, minimizing idle time. Now I need to talk about fair resource distribution. Like resources like the CPU time, memory, I/O devices are allocated fairly to processes, avoiding issues like starvation and deadlock. These mechanisms ensure that multiple users and processes can work efficiently in a shared environment. Now, security and protection. The OS also serves as a gatekeeper, ensuring processes are protected from the unauthorized access. Data is managed securely to prevent leaks and breaches. Malware or faulty programs don't disrupt the system. For example, modern OS include firewalls, permission systems, the encryption to safeguard user data and system stability. Now I'd like to talk about the I/O management. The input-output management is vital for handling communication between the hardware and software. The OS allocates resources to devices like printer, the keyboard, and monitor, synchronizes data flow to avoid bottleneck, provides the device driver that abstract hardware complexity, allowing application to interact seamlessly with the I/O devices. For instance, when you print a document, the OS ensures the printer gets the necessary document without interrupting other processes. Now, I'd like to talk about abstract hardware complexity. The OS abstract hardware complexity by providing user-friendly interface, managing hardware resources, and handling in device interaction, enabling the application to access hardware without low-level management. Now, OS as a resource manager, task manager example. A great example of OS as a resource manager is the task manager. It provides a GUI for monitoring running application and background services, system performance, and resource utilization like the CPU and RAM uses, networking activities, and user sessions. This tool highlights how OS oversees resources and provides transparency to the user. Now, process control block. Lastly, the OS tracks every process using a process control block (PCB). The PCB stores crucial information that includes the process state, the program counter and the CPU register values, the memory allocation and I/O status. The PCB ensures that the processes can pause and resume seamlessly, maintaining system efficiency. That's all for me.
Let's talk about the evolution of operating systems. The first generation of computers from the 1940s to the 1950s. For more than a decade, the computing systems developed did not support any OS, and the users had to manually feed the program and the data. Now, this period is also called the open shop phase. Each user was allotted a fixed amount of time to use the computer, and mostly the time for setting up of computer was much higher than the actual time of the computation. This exercise was extremely laborious and error prone. The IBM 701 machine is an example of an open shop machine, as you can see right here. The first electronic computer came in 1940 to replace the mechanical computer. It did not have any OS and was used to do simple calculations using plug boards. The IBM 701 also had a plug board, as you can see right here. Any kind of computation had to be manually programmed by wiring the plug boards together. It was indeed a laborious process. We move on to the second generation of computers from the 1955 to 1965. The users were asked to prepare their job or the process in punch cards of programs and data. And then they were asked to submit this to the operators who run the jobs on the user's behalf. Similar jobs, based on requirement of similar set of resources, were put in a batch, and these jobs were scheduled for execution sequentially, one after another, batch-wise. As you can see right here, a person is preparing out their punch cards and giving it to the computer operator, who then loaded up all of these punch cards in sequence and executed them one by one on the computers. This phase of computing is also called as closed shop, as users were not allowed in the computer room. It is also called batch processing, since processes were computed in batches. Even though it was much improved over the open shop era of the 1940s, it was still plagued by slow speed of I/O devices. The share operating system for the IBM 709, which is shown in this picture, was an early batch processing system. It took ages to set up the computer for processing before the processing actually took place. This was done by appointing skilled professionals, also called computer operators, in the computer room, as you can see right here. Now, what could be improved from the second generation of computers? Well, the batch processing system automated the task of making the manually plugging in wires on the plug board. You no longer needed to plug in the wires manually. You could just prepare batches of processes and give it to the computer operator. However, as computers became more and more popular, they found their way to schools and universities and public offices. It became cumbersome to program specific instructions in assembly for each new I/O device introduced in the market. Think about it this way. In different schools and hospitals, there were new products being launched, like some new printer, and this printer needed their own set of programming to make it work with the existing computers. So every time there was a new printer, the programmers needed to be called to build or write programs specific to that printer so that it works with the existing system. And this is where the idea of device drivers in modern operating systems arose. Also, there was the issue of CPU idling. When one program went for an I/O operation, which is like taking input or displaying or printing output, the CPU remained idle, since it waited for the program to come back to execution. This was due to the fact that sequential execution in batch processing forced the computer processor to stall or remain idle during an I/O operation, which eventually led to poor utilization of CPU time. Of course, the CPU was sitting idle when it could have processed something else. We will get to that, and in fact, in the third generation of computer, this is what improved. Key technological advancements from 1965 to the 80s in the third generation of computers included large core memories of CPUs, secondary storage device with random access, and bigger data channels, and the introduction of hardware interrupts. Now, the concept of multi-programming became popular among OSs released in the third generation. Secondary storage device is where the processes were saved when not in execution, and the main memory loaded up all of the jobs or processes at once, like job A, job B, job C, which were sequentially executed by the CPU. As in this diagram, the CPU is currently executing job B, and the job C is waiting for CPU time, right there in the memory. So all of these processes were loaded up in the memory instead of one by one putting in batches of processes. So this was more efficient. It reduced the time wastage in loading up and unloading batches. So multiple programs loaded in memory with interrupts, allowing CPU to switch between tasks. The CPU worked on one program while another waited for the I/O operations. Now, CPU utilization improved, but still lacked interactive user response. Sure, now CPU was to be able to preempt from one process execution to another when that particular process being executed went into some kind of I/O operation, which is slow. So meanwhile, the CPU just switched into some other job. So the CPU utilization became much better. However, there was still an issue of interactive user response, which we'll come to. The concept of time-sharing operating systems arose. Over here, the CPU could switch between, let's say, process 4 and process 5 after a set amount of time. So let's say process 4 is an active state. It's going to run for 2 nanoseconds, and then after 2 nanoseconds, the CPU switches from process 4 and context switches into process 5. And after another 2 nanoseconds of execution of process 5, it switches to process 6, and so on. The CPU keeps switching between processes regardless of if there is time remaining on them or not. So this enabled interaction between users and the system via multiple terminals. It could have been done because the CPU can now give time to different processes after a set interval of time. This made the CPU look and feel more interactive and responsive. Users experience the illusion of a dedicated processor due to rapid task switching. Examples include compatible time-sharing system, multiplex information and computing service. Now, this generation also introduced file systems, file protection, and passwords. Concurrent programming could now be done to solve issues like deadlocks using synchronization tools like semaphores and monitors. Examples include the operating system. RC4000 introduced by Brinch Hansen in the 1970s. Now let's come to the modern day and look at the modern operating systems, also known as the fourth generation of operating systems and computers. Now, from time sharing to personal computing, advancements in microprocessors and semiconductors during the 1970s made computing affordable for individuals. Shifted from resource efficiency of multi-user systems to user convenience of single-user environment. It gave rise to the personal computing era, the rise of single-user operating systems. It introduced graphical user interface, GUI, for easier interaction through mouse clicks. You could now see on the screen what the buttons are, what the windows are, and you can interact with them It gave us a familiar kind of interface to use the computer instead of the previous terminal like systems, which gave us a command line interface. GUIs were much more user friendly, and this allowed computers to be able to be used by the common person. The fourth generation operating systems included MS DOS, Windows 95, and Apple's Macintosh. Over here, you can see the overall structure of the operating system. It included a microkernel with memory management, CPU scheduling, and inter-process communications, and the hardware, the metal itself. And all of this stuff in the microkernel is in kernel mode, and this stuff, the device drivers, the file systems, the application programs, they're in user mode. There is a separation of user mode and kernel modes, and this will be discussed later on. Here are some examples of modern day operating systems: Arch Linux on desktop computers, Android on portable computers like smartphones, Ubuntu as a part of Linux, just like Arch Linux, on desktop computers, of course, Mac OS on Apple computers, and Windows 11 on most of the computers in the world by Microsoft. Now, key features of modern operating systems focus on user experience, accessibility, and ease of use. It enhanced multitasking, seamless user interaction with sophisticated interfaces. Technological advancements like powerful processors, memory management, and development of GUIs further accelerated development of these modern operating systems. And the fact that personal computing became more mainstream and accessible, shaping the technology landscape. Evolution of operating systems with continuous updates and improvements. Next up is types of operating systems.
Systems are the cornerstone of computing, responsible for managing hardware resources, software processes, and providing an interface for users to interact with the system. Different types of operating systems have been developed to cater to diverse computational needs and use cases. The first type of operating systems that will be discussed is batch operating system. Batch processing systems are designed to execute groups of similar tasks referred to as batches without requiring user interaction during execution. These systems aim to automate repetitive processes, ensuring efficiency and consistency. Characteristics of batch processing systems. Task automation. Jobs are submitted, queued, and executed without requiring user input after initiation. Scheduled execution. Tasks are typically scheduled during off-peak hours to optimize resource utilization. Sequential processing. Jobs within a batch are executed in a predetermined sequence or based on priority. The advantages include high efficiency in processing large volumes of repetitive tasks. Secondly, minimal human intervention reduces the likelihood of errors. Thirdly, it allows optimal utilization of system resources by executing jobs during idle periods. Challenges: lack of real-time feedback, errors, or issues are identified only after processing. Also, it is not suitable for dynamic tasks requiring immediate responses or user inputs. Next, we have the layered operating system. The layered operating systems are structured hierarchically, dividing the system into layers with each layer performing specific functions. This modular approach simplifies design, debugging, and maintenance. Structure of the layered operating system. First, hardware layer. It has interfaces directly it interfaces directly with the physical hardware components. Second, kernel layer. It manages core system functions like process scheduling, memory management, and device control. Third, service layer. It provides essential services such as file management and I/O operations. Fourth, user interface layer. It serves as the interaction point between the user and the system, including graphical or command line interfaces. Key features include modularity. Each layer has well-defined responsibilities, improving system organization. Secondly, isolation. Communication between layers is restricted to adjacent ones, preventing cascading failures. Thirdly, ease of maintenance. Errors are confined to specific layers, simplifying troubleshooting and updates. The advantages include clear separation of concerns, which enhances reliability and security. Simplified addition of new functionalities without disrupting existing layers. Thirdly, this makes the system scalable for future enhancements. The challenges include increased overhead due to interlayer communication, and designing a well-structured system with optimal layers also requires careful planning and expertise. Next, interactive operating systems. Interactive operating systems are designed to facilitate real-time interaction between users and the computer system. They prioritize user experience, providing immediate responses to inputs. The characteristics of interactive operating systems: real-time feedback. Commands or inputs from users are processed and results are displayed instantly. Time sharing. The system allocates CPU time to multiple tasks or users in rapid succession, maintaining responsiveness. Thirdly, user engagement. These systems focus on enhancing the ease of use and interactivity, often using graphical interfaces. Key features: firstly, preemptive multitasking. Ensures responsiveness by allocating CPU resources based on task priority. Secondly, resource management. Efficiently manages multiple concurrent processes to prevent resource bottlenecks. Thirdly, dynamic interaction. Users can alter processes or inputs during execution without disrupting the system. Advantages are: firstly, this improves productivity for tasks requiring continuous user engagement. Also, it facilitates real-time debugging, editing, and process control. The challenges include high system resource consumption, especially under heavy user loads. Secondly, this requires sophisticated design to balance responsiveness and system stability. Coming on, hybrid operating systems. Hybrid operating systems combine the features of batch and interactive systems, aiming to achieve a balance between efficiency and user interactivity. These systems are designed for modern computing environments with diverse workloads. Characteristics of the hybrid operating systems. Firstly, concurrent operations. It supports simultaneous execution of real-time user processes and background batch jobs. Secondly, dynamic resource allocation. Adapts resource usage based on workload priorities, ensuring smooth operation for both interactive and background tasks. Thirdly, scalability. Can accommodate varying workloads without significant performance degradation. Key features include process scheduling. Efficiently schedules tasks to prevent conflicts between real-time and batch processes. Secondly, integrated design. Combines elements of multitasking, batch processing, and real-time responsiveness. Thirdly, flexibility. Supports a wide range of applications from personal computing to enterprise solutions. The advantages of this operating system include it provides a balanced system suitable for both automated and interactive tasks. Secondly, it enhances overall efficiency by leveraging the strengths of both batch and interactive processing models. The challenges include: firstly, complex resource management can lead to potential bottlenecks. Secondly, it is really tough to maintain optimal performance for diverse workloads which requires careful system tuning. Next, real-time operating systems. Real-time operating systems, or RTOS, are designed for environments where precise timing and predictability are critical. These systems prioritize task execution within strict time constraints, ensuring reliability and determinism. Characteristics of the real-time operating systems. Firstly, deterministic behavior. Ensures predictable execution of tasks based on predefined schedules. Secondly, priority-based scheduling. Critical tasks are assigned higher priorities and executed ahead of less critical ones. Thirdly, minimal latency, which guarantees rapid response times for time-sensitive operations. Types of real-time operating systems. Firstly, the hard real-time systems, which strictly adhere to deadlines used in safety-critical applications like medical devices and industrial controls. Secondly, soft real-time systems, which allow minor deviations from deadlines suitable for applications like multimedia streaming. The advantages include reliable and predictable task execution, and secondly, it is essential for applications with stringent timing requirements.
Distributed operating system manages multiple independent computers to work as a single system.
In a distributed operating system, each unit shares resources like their processing power, memory, and storage, resulting in better efficiency and faster execution of processes. This type of OS enhances scalability and resource optimization as new units can be added to the OS as per the user needs. In distributed systems, they connect independent computers via networks and enable resource sharing. They also facilitate communication between these systems through methods like message passing and RPC, allowing the systems to interact with each other. They also implement fault tolerant mechanisms to maintain reliability and safe execution of operations. Distributed operating systems are vital for handling complex, large scale operations across high demand environments. Embedded operating systems. An embedded operating system is designed to handle some specific operations within a larger machine, like an automobile, a medical device, or any other home appliance. Unlike other operating systems, embedded operating systems are lightweight, efficient, and tailored for the specific hardware, ensuring low power consumption and faster response times. They're designed for specific tasks, emphasizing efficiency and minimal resource usage with giving real-time performance. They often have limited user interfaces and are integrated into their own hardware devices, ensuring reliable operation and low power consumption. Embedded operating systems are streamlined to learn essential functions with minimal resource use, focusing on stability and reliability in situations where precise and uninterrupted operations are crucial for performance. Now we will understand how multiprogramming and multitasking operating systems work. So let's start with multiprogramming. Multiprogramming is a system which allows multiple processes to run simultaneously by loading all of them into the main memory all at once. This execution is non preemptive, which means that all the programs continuously run one after the other completion. However, if the current process in the CPU has to leave the CPU and go to a particular input output device for some hardware operation, the next process immediately takes its spot in the CPU, which leads to lesser wait time and more CPU efficiency in case of multiprogramming. Multitasking. Multitasking is a system which allows multiple processes to run simultaneously by allowing each process to run for a specific time and then switching to the next process, irrespective of whether the current process is complete or not. This execution is preemptive, which means that all processes run for some fixed time and then switches to the next process, irrespective of completion. This leads to a faster response time, enhanced user productivity, and higher CPU utilization in multitasking. Multitasking involves switching between tasks, which gives an impression that multiple applications are running simultaneously. It also involves time sharing, which ensures that each application receives a fair share. Multitasking can also include features which declare the priority of each process so that the system can operate and provide time to each process individually and particularly according to their importance. However, even though multitasking is advantageous, the process scheduling is difficult. So the differences between the two types of systems. Firstly, multitasking is preemptive while multiprogramming is non preemptive. This means that multitasking can handle the execution of multiple processes simultaneously, while in multiprogramming, only one process is executed at a time. Also, although both multitasking and multiprogramming increase CPU utilization, multitasking does it by increasing responsiveness of the CPU, while multiprogramming does it by organizing jobs. Now, multitasking uses time sharing mechanisms like SRTF and round robin so that multiple tasks can run at the same time. Multiprogramming, on the other hand, uses job scheduling algorithms like FCFS and SJF so that more than one program can run at the same time. Multitasking, due to these time sharing mechanisms, can give a feel that multiple processes and or multiple applications are running at the same time, since each process is executed for some fixed amount of time before switching to the next one. However, in multiprogramming, only one process is executed at a time, which means that the CPU can go to the other process only when the current process has stopped executing, or in other words, terminated. Now, lastly, in multitasking, the execution of process is faster than the similar execution of processes in multiprogramming, which is slower than multitasking.
So, I will now be continuing this presentation about operating systems. My topic for today is what are user and kernel modes and why is it required. So, let's start. So, user mode is the mode which the user interacts with, and it's a mode which doesn't really have any privileges with the OS, and anytime it wants to execute anything to the system level, so what it has to do is send a system call which invokes the kernel mode and allows the operating system to execute the request of the user, and this is how most operating systems today work, and its benefits mainly are increased security and reduced risks, and the user can't really do anything which would completely destroy the processes of the operating system and basically lead to a crash. So this is what the user mode is, and this is the kernel mode. So the kernel mode has all the access privileges and stuff to the OS, and it can execute any CPU instruction. And user mode applications always rely on this kernel mode to perform anything, because anything that requires higher privileges, you have to use kernel mode. So now this slide explains the link between user and kernel mode. So as I explained, what the user mode does is invokes a system call. So anything requiring like stuff like hardware control and other things, these are only restricted to the OS, like only the OS can execute them. So if a user application ever needs to do this, so it needs a permission to like go into the like kernel mode and execute the instruction. So any attempts to execute these instructions directly invokes a system call to the kernel mode. So this just safeguards our systems and increases the security. So yeah, so this is how it's executed. So there's a mode bit which like 0 is for kernel mode and 1 is for user mode, and it helps distinguish the OS of which mode is currently active. So and like when it's booting, the OS begins in kernel mode, and it boots and then shifts control to user mode, and every time a user has to perform any instruction which requires higher, more privileged accesses, then it switches by a system call. Thank you, and hope you liked our presentation.